Assalamu alaikum. My name is Eng.Khaled and my supervisor is Professor Abdullah Al-Aidad. Our research named as Wide Area Protection Scheme for Active Distribution Network Aided Micro-PMU. The abstract: this research proposes a modified wide area protection scheme based on the ratio of the sum of voltage phasor across two terminals of transmission line to the sum of the current phasor flowing in the line. The modified protection scheme has been tested in the distribution system with different fault type and different operation modes. Some introduction about active distribution network. Firstly, the DG's integration to the distribution network will convert the traditional distribution network to be an active. Additionally, this integration may use to formulate microgrid. And one of the major issues of microgrid is the protection system. That because the fault current varies according to the mode of operation of microgrid. About the wide area protection, the rapid development of communication system and the ability to precisely measure the electric quantity encouraged many researchers to suggest a new protection scheme named as wide area protection scheme. About research problem or problem statements, this research modified wide area protection scheme which is able to detect all type of fault and able to achieve a proper coordination between the primary and backup protection in radial active distribution system. And about the research methodology of our study, this research modified the wide area protection scheme based on micro-PMU measurement and integrated impedance angle to generate a tripping signal for specific relays. Because our methodology based on integrated impedance angle, we must define what's the integrated impedance firstly. The integrated impedance is the ratio of the sum of voltage phasor across two terminals of transmission line to the sum of the current phasor passing through the same line. This is the sum of voltage phasors and this is the sum of current phasors, where V1 is voltage phasor at bus 1 and V2 is voltage phasor at bus 2. Now, if a fault is applied in the middle of the transmission line, the positive sequence impedance can be presented. It can be presented as a following network, where VF1 is the voltage at fault point and UF is the positive sequence network voltage source. And by applying Kirchhoff voltage law at loop 1 and loop 2, the V1 and V2 can be calculated, where VF1 is minus I12 multiplied with the grid impedance and Z1. Now, by substitute the previous equations in the general equation of integrated impedance, the general equation of the integrated impedance for the previous system can be calculated. Now the angle of this impedance is the integrated impedance angle. There are some notes about the integrated impedance angle must be noted. Firstly, the angle of integrated impedance will be negative if the internal fault occurs between bus 1 and bus 2, and the angle of integrated impedance will be positive if an external fault occurs. The no fault situation is like to the external fault. That means the integrated impedance angle will be positive. Now, about the principles of proposed protection scheme, it's assumed that micro-PMU is already installed at each bus in the distribution system, and the micro-PMU continuously sends the synchro-phasor measurement of voltage and current in real time to the wide area control center. In the control center, the integrated impedance angle will be calculated and the tripping signal is generated and sent to the specific primary protection relay. This tripping signal without time delay, and the tripping signal with predetermined time delay is sent to the backup protection relay. Now, the faulty section in the distribution system is determined in control center as the following equation by proposed scheme. This equation mainly based on the sign of integrated impedance angle. If the sign of integrated impedance angle is less than 0, that means the variable f will be 0. And if it's larger than 0, the variable f will be 1, where variable f is presented the transmission line status. And the operation time for each relay is determined in the control center based on the following equation, where this equation, in this equation, the variable CTI is the coordination time interval, which is 0.2 in this study, and F forward is the summation of transmission line status, which are downstream the transmission line under study. Now, for a better understanding of proposed scheme, a simple distribution feeder which consists of 3 transmission lines is shown in the figure. This is transmission line 1, 2, and 3. Now, when a fault is applied at transmission line 3, the variable F3 will be 0 because there is a fault in the transmission line 3, and the variable F2 will be 1, and the variable of transmission line 1, which is F1, will be also 1. The operation time of primary protection relay R4 and R5 can be calculated as previous equation. The CTI variable, as stated previously, it's 0.2, and the variable F3 will be 0. That means that this term will be 0, and the operation time of R3 and R4 and R5 will be 0.2 seconds. Similarly, the operation time for R2 and R3 can be calculated, which is about 0.4 seconds. Finally, the operation time of R1 can be calculated, which is 0.6 seconds. In terms of time delay of the proposed scheme, the time delay needed to integrated impedance angle to cross the threshold value is about 20 milliseconds, and the calculation of integrated impedance angle and the value F in the control center needed about 20 microseconds and 10 microseconds for calculate the operation time for all relays, and about 8 to 11 milliseconds as a communication latency based on the IEEE standard 61850. Then the tripping signal can be generated. To test and validate the proposed scheme, we take a case study. Our case study is a medium voltage distribution system with different scenarios, different faults, and different operation conditions. This system is our case study. This system connected to the grid with bus 1, and this system has 4 DGs, DG1, DG2, 3, and 4. The capacity of DG1 and DG2 is 2 megavolt ampere, and the capacity of DG3 is 1.5 megavolt ampere, and finally the capacity of DG4 is 3 megavolt ampere. In this system, there are 2 fault points has been chosen. The first fault point in transmission line 2, and the second fault point at transmission line L40. There are different scenarios and different fault type has been applied at this fault point. Result and discussion. This figure presents the response of integrated impedance angle with respect to the time in second when different fault types applied at fault point number 1. Firstly, the largest time needed for integrated impedance to cross the threshold value was for phase to ground fault, which is about 6 milliseconds. And the lowest response time was about 2 milliseconds, which is for 3 phase to ground fault. This table presents the operation time for backup and primary relay when different fault type is applied at point 1. We must be noted the operation time is probably coordinated between primary and backup relay. The backup relay is the primary protection is R2 and R5, and the backup relay is R1. Now, to test the performance of proposed scheme for a high impedance fault, then a single phase to ground fault has been applied at fault point number 1 with different fault resistance. For example, 0.1 ohm, 10 ohm, 11 ohm fault resistance have been chosen to test this. Now we must be noted that the response time of integrated impedance angle increases when the fault resistance increases. and the maximum response time is about 50 milliseconds for a fault resistance 100 ohms. This table presents the operation time for all protection relay when a single phase to ground fault is applied at fault point 1 with different fault resistance. We must be noted here all primary and backup protection is properly coordinated with the coordination time interval, which is about 0.2 seconds. For more investigation, a different fault type is applied at fault point 2. Similarly, all coordination time between primary and backup protection is properly coordinated with 0.2. Here, to ensure the proposed scheme able to discriminate between the fault and the non-fault situation, such as island situation, an island is applied at 0.1 second by opening the gate breaker. If the integrated impedance angle response decreases to the threshold value, a mere operation may occur. This is the integrated impedance angle response when island is applied at 0.1 second. We must be noted here that the integrated impedance angle does not reach to the threshold value. That means there is no mere operation will occur by the proposed scheme. Finally, some conclusions. Firstly, the proposed scheme based on the integrated impedance angle, and the proposed scheme has been tested and validated by a distribution system using MATLAB simulating program with different fault type, different fault resistance, and different operation condition, including island situation. And based on the simulation result, the modification on wide area protection scheme able to achieve a proper coordination between the primary and backup protection, and it's able to generate tripping signals for with acceptable time delay does not exceed 31 milliseconds, which is suitable for smart distribution system protection applications. Finally, thank you for your listening.